Hey, kids, we're going to go through the second part or second half of this Unit 5, Lesson 3, which is Speed and Motion today. And today's a lot of math, so Mrs. Pratt will be happy for us. But I'm going to go through problems with you. So be patient and please listen to the whole presentation because it's really important and there's some terms you really need to know. Okay, we left off my gosh, I guess it was last Thursday, with how you know average speed. Okay, so let's look at this problem. A penguin swimming underwater goes 20 meters in 8 seconds. So let's look at the average speed. Well, we know the distance is 20 meters and the time is 8 seconds. We want to know the average speed. Okay, so they have us draw a sketch. For a lot of these problems, if we were doing them in a real book, if we weren't remote or hybrid, they put the distance on the top and the time below it. Okay, so speed equals distance divided by time. That's what that line is. I know you know it, but just reviewing it. So then we always substitute in the formulas. So speed is 20 meters over 8 seconds. And if you would do the math, you would find out with a calculator. And people have asked in my room, you can always, forever and for always, till May 31st or whenever our last day together is, use a calculator in my room. Okay? So anyhow, and also you can use one. It comes up on those Canvas questions. So if you ever need one, it's there for you to use. All right. So 20 divided by 8 is 2.5. They always want you to worry about the degrees. In this case, it would be meters per second. That line means per in this case, so meters per second. So your answer is 2.5 meters per second, okay? The penguin is going every second. They're going 2.5 meters. All right, so now we're going to do one on our own. So we have a runner, and their time for a 100-meter race is 13.75 seconds. So we're going to look at the average speed. So the first thing they want to know is, what do you know? Well, let's get a pen here. Okay, we know that it's 100 meters, and we know that it's 13.75 seconds. Let's get that changed back. Okay, so we know 100 meters, and we know that it's 13.75. What do we want to find out? We want to know her average speed. Maybe. All right, so average speed. So they want us to draw on the label the sketch just like before. So the distance is on top, 100 meters, and there is her time, 13.75. What would our formula be? Say it to yourself. Speed equals distance over time. Speed equals distance per divided by time. So now we're going to sub the numbers in. So do we know speed? No, but we know the distance. So it's 100 divided by the time, 13.75. All right, calculate. So if we had a calculator, that would be 7.3 meters per second. So you make sure those agree. They agree. So the answer, if you were doing this problem, is 7.3 meters per second. All right. Now we're going to look at constant speed. Now, how I always think about this is if your parents or whoever you were in a car with, if they put on the cruise control, sometimes I do when I'm on a highway so I don't get a speeding ticket. And if you hit the cruise control in your car, then say you're at 55, so let's say we're going the speed limit, it would keep you at 55 miles per hour. Okay? So if you use what is called a distance time graph, and this is very important for you to understand. This is one of our objectives, how to read and or create a distance time graph. That will show us the distance and the speed change over time. Okay? So here we go. So some of you know this from what we've talked about in the past, but to review, if you've not done it yet in math or you forget, the up and down is the y-axis. So that is always the distance on a distance time graph. The X, as you can see, the X is across, that is time. Okay, so now we're going to look at these more. Move my face, sorry. If an object is moving at a constant speed, the graph is a straight line. So again, if you were in a car that's going 55 miles an hour the entire time, you're going to have a straight line. It's uniform. So as your time goes up, the distance goes up. So if it is a straight line out of where these two meet, the point here, that is it shows constant speed. All right. The next point we need to talk about is this. The steepness or the slope of the line can be used to determine the average speed. This is a little bit higher level math, but some of you might know what I'm talking about. So, average speed can be calculated by dividing the change in the distance by the change in the time. And again, we'll look at those. Don't panic. All right. So here we have an example. Okay. So, here's the change in y. So if you go clear up to the top, y has gone from 0. Let me see here. It says laser pointer. I don't know if that's true. Oh, it's awesome. You have 0 here and 140 up here. Okay, so that is here's your 140. That is your change in y. And if we, I keep needing to move me. Sorry. If we come down here on the X, you see that that's at 10. If you come straight down here, 10. So your change in X is 10. All right. So actually, they're doing these 2 points. You could have done it from 0, but that's okay. All right. So your change in Y, you're ending at 140. You're starting here at what they say 70. So 140 minus 70 is 70. If you would come down here in a straight line, this would be at 5. So you've gone from 5 in between 4 and 6 to 10. So that is your change. So 70 divided by 5 is 14. So that would be your average speed. Okay. Okay, now we're going to make one of our own. So an ant is walking at a constant speed of 30 centimeters per minute. That's not very much. We're going to fill out the table, and then there's going to be this distance time graph if it were to walk for 6 minutes. So let's start here at the beginning of time, which would be 0. And how far is it gone in 0? Is it second? 0 minutes would be 0 centimeters. Okay. Oh, now it went on. Okay. So as it tells you, it's a constant speed of 30. So in 1 minute, it's going to 30. And we will, let's do this. Okay. So 30 is about here. Okay. In 2 minutes, we are up to 60, which would be roughly in here. We'll see how close I get when it gives us the answers. There we go. Pen is P. Okay. Then lastly, in 3 minutes, we are up to 90, which is just here below the 100. Okay. So if we were to draw the line, we'll see how close my points are to the line. Oh, pretty close. Okay. So that's constant speed. It leaves from this corner and goes at a straight up diagonal line. Okay, and then they've also charted all the points, which we've done over here. Okay, now if you have changing speeds, like pretend you're going to Columbus. Well, you get out of your driveway, you get however you go to Columbus. For me, it would be going down Route 423 to Waldo. So you get up kind of good speed, and then you have to slow back down in Waldo to stop, that little town there. If you don't know what Waldo is, then you get back on the highway and you start speeding up again. So you're constantly changing speed. So those lines are different. It's not that straight line I just showed you, okay? They go up and down. So Curved lines indicate or show that objects are changing speed. So that would be a curved line. And again, here's an example. Now remember before, for constant speed, it was more like this, and that's terrible, I'm sorry. But see how much steeper this is, more straight up? That means your person or whatever is going faster. This is steady or constant. If it is straight, that is stationary, okay? And then going down would be slowing down, obviously. Okay, so let's look at this question. If a line on a distance time graph, again, that's what this is, becomes steeper, so the green line, what has happened to the speed of the object? Well, it tells us it's getting faster. What if it is flat? Okay, well, then that means it's steady or stationary. So that's exactly what they have. The speed of the object has increased, but a flat line indicates an object is not moving. Okay. All right. So they want us to complete this graph. They've given you the points 1 and 10, 3 and 10, and 4 goes up to 30. So that would be up here. And then 5 is 50. So we have a straight line where it's not moving, and then, whoops, we go up from there. Okay, so you would see that the speed is changing. All right, we're going to go over this real quickly. We've already done one of these problems. Okay, last thing I want you to know for today is the term velocity, and you have looked at these with Newton's laws. Okay, so the direction of the motion must be included in a measurement for a moving object. Okay, so any quantity that has size and direction is called a vector. Velocity is speed and direction. Vector is size and direction. Okay, speed and direction are velocity. Okay, so this is a great point for you to know. Objects cannot be moving at the same speed. So on this chairlift, everyone's going at the same speed. They have to because they're a set distance apart, but they have different velocities. Okay, these people are coming towards us. Those people are going away. All right, and lastly, and then we'll stop for today. Here's a Venn diagram. I'm pretty sure you know how to do these, but this circle is, this part is speed alone. This part is velocity alone. And where the sectors, or where the circles, intersect, that is both speed and velocity. So let's think of a statement for this. For speed, speed is a distance and a time, how fast you're getting somewhere. Velocity is distance and a time and the direction. So you're going south or to the right or whatever. Both of them together describes how fast something moves. So those are terms you need to know. All right, we will stop there for now. You will have a few questions about today's presentation. As always, reach out to me if you need me. I'm going to be really on you guys about keeping up with your work. Again, most of you are doing great. Keep it up. I'm really proud of you. And we will talk on Friday.